And now we're given this proof or a theorem that says if M is an element of a real number such that the absolute value of L minus M is less than E for all E, which is an epsilon greater than 0, then L will be equal to M. Then this proof is the same thing as having if the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of f of x equals to M, then this would mean that L is equal to M. Then for us to prove this, we need to prove by a contradiction. Yes, right. We need to prove by contradiction. And to prove this by contradiction, this would mean that we need to prove this. Here we're given P implies Q, right? As we should do this, we should assume P and negation of Q. You see, right? So we're going to do this. We're going to, let me erase this. All right. P and negation of Q. So first I'm going to check which one is my P, which is this, Q, which is this. See, right? So I'm going to assume L M element of a real number such that the absolute value of L minus M is less than E for all E greater than 0, then I write end. Now I'm interpreting this sign as the end. I don't write then, I write end. So I negate Q. Our Q is L equals to M in this case. So I'm going to negate Q. I'm going to write L is not equal to M. And what does this mean? This simply means that L is either less than M or L is either greater than M. You see, right? So in this case, I can try to show this. What do they mean? Right? I'm going to take these cases. I'm going to say case 1. If L is less than M, then what will happen? So we're going to say if L is less than M, this would imply that the absolute value of L minus M will be equal to, check, L is less than M, right? So it means that this would always be negative. So we're going to take the negative part of it. And then this would mean that if I distribute the negative, this would be positive M minus L. And since M is greater than L, this will always be positive. You see, right? Then we check case 2. We say if L is greater than M, then this would imply that the absolute value of L minus M. So check this, since L is greater than M, this would always be positive. So I'm going to take L minus M would be greater than what? 0. So when we come back here, we realize that we have M minus L and L minus M. So if there's, let's say there's minus A here and A here, and this is like this, and there's something here, this would mean that the absolute value of that thing is less than A, right? So in this case, as we could consider this as the negative part and the positive part, so we can take this as the absolute value. We can take this as the absolute value. So we're going to say this would imply that the absolute value of L minus M is greater than what? 0. And since this is greater than 0, right? And what do we know else? Also, we know that E is greater than what? 0. So, and again, E is greater than this. You see, right? So if I was to say this, if I was to let E be equals to the absolute value of L minus M over 2, I said that this is greater than 0. So if I was to say this, I can just let this assumption. So when we want to disprove something, we're always going to let E be something, right? So in this case, we can choose it to be L minus M, we divide that by 2. So in most cases, we just let E be equals to 1. So now we can do this, right? Since we have this case, all along I was doing all these things just to find this case. So what I can do is I can go back to my assumption. Remember here I assumed that Lm element of a real number. So those will have only okay if we have this. You see that? So I can come and say since the limit as x approaches c of f of x is equals to L, then I say for each. So I can just decide to say for each E, because I said that E is equals what? L minus M over 2. This would be greater than 0. We agree, right? They exist So here there would exist what? There would exist a number. It can be, if we were talking about SMT01, would say that there would exist a delta. Then if it's a calculus, advanced calculus, would talk about they exist n. Alright. So there would exist this number, which is a what? A positive number, element of a natural number. We agree, right? And this would be subscript to 1. So there would exist this number such that for all n greater than this subscript 1 would have, so I would write f of x minus L, which this would be, it should be less than E, we agree, right? But what is E? In this case, E is L minus M over 2, we agree, right? And again, I take the other part, I'm gonna do the same thing. I take the other part, I'm gonna do the same thing. And on the other part, I'm also gonna say since the limit as x approaches 0 of f of x is equals to m, right? I say for each e equals to the absolute value of L minus M all over 2 is greater than 0, right? And then I would say they exist in two elements of a natural number such that for all n greater than 2, this would imply, and I take the absolute value of this minus this, f of x minus m, right, which is less than, we know that this should be equals less than E, but then you know that E is equals to what? L minus M over 2, right? So now I have this. So since I have this, I can now let n be equals to, you can choose max or you can choose min. So we can choose max, we say, but in this case, since this proof is from first level, we can choose min. We're saying that this should be the smallest positive integer. So we can choose mean. We may choose this to be the smallest positive integer. We have n1 and 2, right? We spoke of n1 and n2. And then now we have this, right? So we're going to now say, since we have arrived to this case, we must now check this contradiction. We must now check L minus M. What will it be equals to, right? Then we're going to have the absolute value of L minus M, which is equals to, and then L minus, we add f of x, we also subtract it. And then by triangle inequality, we'll have L minus f of x plus f of x minus m. We agree, right? Then this, we know that it's less than, and this, it's less than e, which is L minus m over 2. So we're going to say that this is less than absolute value of L minus m over 2 plus L minus m over 2. And this would be equals to L minus m. So the value of L minus m, right? So check this. Here we're saying this, right? This is saying that the absolute value of L minus m is less than the absolute value of L minus m. So check this. This is a contradiction, right? So because these two are not like that. This is not less than that, they're equal. So there's a contradiction, which I would then come and say, thus the absolute value of L minus m is less than the absolute value of L minus m, which contradicts our assumption. You see, right? This contradicts our assumption. So we say, therefore, yeah, I can just say, therefore, L is also M. Then we're done with this proof.